All right. I appreciate everyone filling out that poll. Going to end that right now, and let's get started. So just to get started here, to introduce myself, my name is David Grafton. I'm the GIS analyst over here at Bad Elf. Today, we'll just be covering the fundamentals of datums. I'm sure some of you have heard of them before, but maybe not quite have a full understanding of the logic behind them, why they're needed, how they're calculated, the history behind it. So we'll be covering all that from A to B. This meeting is being recorded and will be posted to our YouTube channel. So if you want to reference it later, you can definitely check that out. It's just the Bad Elf on Bad Elf GPS on YouTube, as well as we'll be hosting a Q&A at the end too. So the actual presentation should take just about 20 to 30 minutes. So definitely plenty of times for questions if anyone has any. So let's go ahead and get started here. I'm going to turn my video off. Let's get the poll out of the way here. So yeah, just the plan for today. First, we're going to start off with coordinate systems. It's really the basis of everything we're doing here. So what is a coordinate system? It's obviously just numbers that reference a unique point. And we need this to take measurements between points to find out how they relate to each other. They'll move on to horizontal datums. They would cover the different models, how they change with time, the differences between them, how they're created, and as well as vertical datums as well. So there's horizontal datums as well as vertical datums. So if you're interested in elevations, we'll cover how to calculate those and make sure you have all the metadata on your next project so you're getting accurate results as far as that goes. Then we'll cover how to transform between the two, and we'll do a little demonstration just showing how you can best not only collect points in different datums, but also transform them from one to another. And then finally, we'll cover projections just a little bit. We're going to be covering a lot of very technical terms today, so I'm not going to dive too much into projections. But datums are the basis of all projections, like UTM, state plane, etc. So we'll just kind of cover how datums relate to those really quick at the end. And then, like I said, at the end, we'll have a bunch of Q&A. So I'm sure you guys will have some questions. Don't hesitate to ask. Looking forward to chatting with you all at the end here. So let's get started. So just starting with the absolute basics, how do we measure locations? So for example, let's pretend we're trying to give someone directions to our house. Smartphones and GPS don't exist. So how are we going to have them navigate to our location? Well, if we just tell them a couple landmarks, like maybe what our house looks like, that's going to be too ambiguous, especially in some of the cookie cutter neighborhoods we have here in Phoenix. You're going to see a lot of very similar looking locations, and it might not really stick out. You know, for example, for a hiking trail, you might see some cairns, but they're not pointing you in a specific direction. It just shows you you're at the right spot. So this doesn't have enough dimensions. So if we increase the dimension from 0 to 1, including a distance element, so maybe we have a landmark and we say, go 1 mile past the big tree or something like that, it still doesn't indicate direction and how you get to that initial reference point. So as I have it here in the slide, it only works if you're starting from a specific point. And then if you, say go to the big tree, past the big tree, a mile through a field, and then that'll get you to my house, well, that still doesn't indicate direction. So that's still not enough information. So finally, if you give somebody your crossroads, for example, Cactus Road and Tatum Road, then that gives you exact location. You can cross-reference both the horizontal and vertical coordinates, and then you can get a specific place to navigate to that location. So that's really the basis we're trying to do here. We're just trying to get a unique set of coordinates that will give you an exact spot. And then you can also compare it with other cross streets. For example, here again in Phoenix, our cross streets are spaced about 1 mile apart. So by just using the numbers and the addresses, you can determine how far you are from one point to another. So it gives that relative distance as well. So obviously just using cross streets isn't quite good enough. We need scale, origin, orientation for exact reference points to get a relative relationship between different coordinates and locations on the planet. So we do this using, starting with math. No one get into it here. We're just some basic algebra stuff. So I'm sure everyone has done this, plotting slopes, He's plotting stuff on a graph, just a simple XY coordinate. So every single projection is going to have an origin with an XY axis. And this is basically how all 2D projections work. For example, UTM, which is, there's, I think, 36, I might be mistaken, zones for both the northern and southern hemisphere, with the origin around the equator. And it gives you northern and easterns with the X and Y. State plane is very similar, but just for more local locations. And township and ranges, for another local example. Here in Phoenix, our township and range system is the system that all original surveys were based off of. And the origin point is right next to our racetrack, Phoenix International, where we just had the championship race a couple of weeks ago. So everything is relative to that. And so anything west of that would be, negative as far as the x-axis goes. Everything right would be positive. So this is great for measuring relative distances, but it does still have some weak points because we do not live on a 2D plane. The Earth is curved. So unfortunately, for any flat earthers who might be attending today, the Earth is not flat. I regret to inform you. If you don't believe me now, I'm sure you'll be convinced by the end of the presentation. Things would be much simpler, so it would be nice if it was flat. But projections need to be created from a 3D model of the Earth. Otherwise, we're just missing too many dimensions, and it is not going to work with the way GPS works. So if we add this third dimension, the Z coordinate, we get this 3D coordinate. And so we have 3 axes. So just like before, we have the x-axis and a y-axis, but now this is actually going to the center of the Earth instead of kind of representing the surface of it. So how the x, y's, and z's work for satellites is that the positive x-axis, that's just going to be a line from the center of the Earth to the prime meridian. So it's gonna just cut right through the middle and intersect with the prime meridian right at the equator. Same thing with the y-axis, but it's just going to be offset by 90 degrees, just going to be perpendicular, and that's going to be intersect the Earth through 90 degrees east, which is about Bangladesh or so. So again, just right through the equator on that plane. And then the z-axis is going to, again, go through the center. The origin of this, all these systems are just based on the center of mass of the planet, or what we think the center of the mass of the planet is, spoiler alert. And then so that's going to be one, the axis that the Earth rotates on, and 2, it's going to be our z-axis for this x, y, and z coordinate system. So this is what's used by satellites since they do rotate around the Earth's center of mass. So this is a perfect coordinate system for them. It's something called the ECEF is what this coordinate system is called. And this pole, that z-axis, is actually not necessarily always the center of the Earth because there is a little bit of a wobble. As you can imagine, the Earth is hurtling through space. There's quite a bit of mass. It's pretty irregular. The center of mass is always not going to remain in one exact place. So to make things simple, we agreed on just one axis, and we just keep that static. So we're not constantly adjusting things. But there's some problems with this. We're looking for practical usage here. We're not computers. We want to just interpret some nice, simple to use coordinates to measure where our assets are. So most coordinate pairs in this system are going to be inside the Earth, which we have no use for. We're not collecting points in the Earth's mantle or deep in the crust or anything. And linear measurements along the Earth's surface are going to involve changes in both the X, Y, and the Z due to the curved surface. So it's going to be extremely difficult to determine what these numbers mean. If these X, Y, and Z's units are in meters, they're going to be extremely large numbers, and it's just not going to mean much to them. So we need a more logical system. Again, we live on a curved planet, more spherical. This is just not going to work for our purposes. Although if we had to make it work, we could, but it'd be very confusing. So just kind of going back, I'm just going to sprinkle in some history as we go through the presentation here. So first datum could actually be attributed to the Greeks way back in about 200 BC. So they used some simple trigonometry to determine the Earth's circumference, which can be kind of probably interpreted to be the Earth's first datum. So all they did, they just measured a distance from a town to a town using ropes. They determined this distance to be 500 miles. And then they just measured the angle of a shadow of a pillar at the same time in both cities. So just using some simple trigonometry, they determined this angle to be 7.2 degrees. in the northern city. And in the southern city that was closer to the equator, the sun was directly overhead, so they had no shadow. So now you have the difference in degrees, which would be 7.2 because it was taken the same exact time. And you also have the distance between the two. So because you know this 7.2 degree difference is equal to 500 miles because they measured it out. And they know that 7.2 degrees is about 1/50th of 360 degrees, which you know is the how many degrees are in a circle. So we're trying to measure the circumference of the Earth. So all you have to do is just multiply 50 times 500, which is equivalent to the 7.2 degrees. And then we get 25,000 miles. And so this is actually extremely close to the actual circumference, which is 24,901 miles, even though they weren't taking into account, you know, all of the specifics, all of the intricacies that go into geodesy when you're trying to measure the shape of the Earth. So pretty amazing stuff for measurements that were taken 2,000 years ago. So basically the Earth's first datum, it doesn't have a lot of aspects of what we see as datums today, but it was a good attempt at measuring the shape of the Earth. So using this system, obviously they used degrees instead of X, Y's, and Z's, and it made things much easier. So angles are much more intuitive when we're working with curved surfaces like the Earth. And so if you ever worked with a polar coordinate system, it's a little bit different from the Cartesian one that we're just working with when you have the X and Y, but it's still just two variables. It's very easy. In fact, if you take some calculus, it actually makes things quite a bit easier for some equations. So all it is just you have your degrees. So you'll have your rotation relative to the origin. So on this example, the origin right here is 0 degrees at the right over here. And then, so you said determine where your point is relative to the rotation. So if you're all the way in the bottom right, you'll be about 300, 330 degrees, top left, 120, 150, and you determine your radius. So in our case, it's even simpler because we're going to be on the surface all the time. So really our radius is just relative to that very outer surface. And that's how we actually get, again, spoiler alert, ellipsoidal heights. So it's actually even simpler for us. And so this, you can do this with both latitude and longitude to kind of, break it up into two different categories, and you'll have a 2D representation of both. So obviously we don't want to have them separate. So we just go ahead and combine them together. The one on the right over here, you'll see you get your longitudes just from placing a circle right at the equator. And then the one at the left over here, you can get your latitudes by doing the same thing. You just place them perpendicular. And then with this coordinate system, you can just combine them together. We'll have degrees for both lat, long, and then our radius, again, is just the distance from that surface from the outside. And so the origin, again, is going to be the center of mass, just 0, 0, 0, center of the Earth. And it's where the prime meridian equator meet is going to be the meeting of the zeros for latitude and longitude. So if you're ever collecting a point and you end up on Knoll Island, that's going to be a place just off the coast of Africa. It's actually a little bit off on this representation, but it's in that Ivory Coast sort of area. And that's just going to be when you might be working with, you might have like projected coordinates and it's supposed to be geographic coordinates or vice versa. It's going to place it right over there because that's the origin of the intersection here. So we combined the two right there. So now we have angular units. It's much easier to understand. It's much more straightforward, better for calculations for us. So now we have to take into account the shape of the Earth. So we have a great way to plot points on a sphere. Unfortunately, the Earth is not spherical. So this was actually discovered by Newton. He discovered this by traveling, and he had extremely accurate clocks for the time, which are kind of a rarity, that were accurate to within a second or so. But he noticed that the pendulum was swinging slower near the equator. And so he was constantly having to adjust his clocks. And what he discovered from this is that the pendulum was actually swinging slower near the equator due to weaker gravity. So the equator actually bulges out a little bit. And anyone who's taken some physics, gravity is weaker the farther you are away from the center of mass. So he was discovered well before his time. It's actually pretty controversial at the time. A lot of scientists disputed with him that the Earth was in fact spherical. I mean, sorry, ellipsoidal. But obviously he ended up being correct. He estimated that was about a 17-mile bulge, and I think it ended up being closer to a 7-mile bulge. But either way, he was correct in his observations. So the shape of the Earth is technically referred to as oblate spheroid. Don't worry about remembering that at all. Everyone just refers to it as an ellipsoid. So it's just a 3D ellipsoid. It's just bulging out at the equator right here. And so in ellipsoids, the wider axis is called the semi-major axis. So that's the equator. And it's going to be bulging out a little bit. Obviously, a lot of these illustrations I'm going to be showing you are exaggerated quite a bit. If you actually look at the difference in meters right here, it's about the order of, let's see, about, sorry, I'm kind of trying to read sideways here, but it should be much more of a bulge, like I said, like 6-7 miles or so. I'm not going to try and do any conversions right now in my head. So yeah, so the Earth's going to rotate around the minor axis at the poles, and yeah, so again, ellipsoid. So that's going to be the key term for today is ellipsoid. That's what all datums are based off. That's what all the calculations are created from. So ellipsoid is the key takeaway from today. So a geodetic datum. So this is a geodetic datum is an ellipsoid that just ties you to real locations on Earth. So as I said before, the origin is going to be the center of mass. This is where all satellites are going to orbit around due to gravity. So this is perfect for GPS, which is completely based off of satellite locations. And but the datum is technically not the same as a coordinate system. So they're often used interchangeably, and it's not a big deal if you use them interchangeably. But honestly, datum is going to be an input into a coordinate system. So coordinate system has a couple of extra components. It's going to have an origin longitude, a prime meridian, like we were talking before, where Null Island is off the coast of Africa. Technically, a datum is not going to have a null because it doesn't have those numbers and have those origin points. It's just the actual model itself. So a coordinate system just adds in a couple extra units, including degree. You could use other units if you wanted to as well. So again, used typically interchangeably with GCS. So North American datum. So the first American ellipsoid was the Clark spheroid created in 1866. So this was the first datum, in North America that it could be interpreted as such. It was created with reference points at 2 ranches in Kansas, given its general central location. So these 2 locations were treated as a 0 height as the reference height, and also established direction as a reference as well. So obviously, since they picked 2 relatively arbitrary locations in Kansas, this datum is going to be extremely biased relative to what we have today. It was regional, but for the time, it was extremely effective and powerful. You got to think for, back then, most engineering projects were more local. GPS was, of course, not a thing. So as long as it gave good local relative accuracy, everything was fine for a regional datum. Today, now we really need international datums. And so including with a North American datum, the current realization, they're trying to align that more and more with the international systems as well. So kind of moving on from that, NAD 27, so this is based on the Clark ellipsoid from the 1800s, same sort of reference points and 0 points and everything. So in the 1800s, surveyors were all across the country installing monuments, these brass caps. These are control points of which everything is based off of for regional surveys, for engineering and scientific projects. And they were all made using leveling techniques. So although they were extremely talented at the time and very brave people, they're often like mountain men going through the wilderness, they did fall victim to distortions. So it was a low accuracy datum. It was, of course, incompatible internationally due to the local ellipsoid, and there just wasn't consistent accuracy across the country as errors mounted up from as the farther you got away from the central datum. Central reference points, the accuracy got worse and worse. But it was an extremely huge project. Over here is 600,000 plus monuments were placed around the country. Many were destroyed, but many survive today. And we'll actually cover how to find some of those and use those in your project. So after that, obviously NAD 27 was not living up to the standards of more modern technology. So we needed a new update. And so we created NAD 83, of which work began in 1974. And this is the datum that we use for survey projects today, although a more updated version of it. So this includes all of North America. In NAD 27, it was just the United States. And this used the GRS 80 ellipsoid. So a more updated ellipsoid that wasn't created in the 1800s. And this was relative to the Earth's center of mass instead of just, local ellipsoid relative to a couple ranches in Kansas. So this used more advanced technology with baselines, used Doppler, some astronomy, which sounds like less advanced technology, but when done right with very sensitive instruments, can actually be incredibly accurate. But originally GPS was not, it was kind of its infancy, so it wasn't developed enough to really see widespread use in the first realization of NAD 83. Again, there's multiple versions of it, so they eventually worked it in, of course. And so this is a geometric datum. This is based on an ellipsoid versus NAD 27, which was a horizontal datum because they just use leveling techniques to go across the Earth's surface instead of basing it on the actual Earth's center of mass. So much more modern system. So mentioned a bunch of terms so far. So just kind of going over the components of datums. Again, a datum is just essentially just an ellipsoid. So if you have slightly different ellipsoids, which are just models of the surface of the Earth, you're going to get slightly different datums. So the main variable is just the center. So typically, we're just going to have the center be the Earth's center of mass, or at least our best guess of it. We're not always correct. The flattening factor is just literally just the ratio between the equator and the pole, and is just how squished essentially the ellipsoid is. If you see these ellipsoids over here on the right, you can see that it's exaggerated quite a bit. In reality, it's just a slight factor, not much. But yeah, different datums can have different amounts of flattening for different models. Also, yeah, so the origin point, it refers to the center. And so these models are going to improve and change with time. So we call these different realizations. So if you see numbers next to your date, whatever datum you're using, so like for example, NAD 83, you might see 1993 next to that, 2011. So they were constantly updating these datums with different versions as technology improves, but also land's going to move around too. The Earth is a living, breathing place with tectonic shifts. More local shifts, subsidence in specific areas as the water table goes down. So all of these factors definitely affect where your coordinates are going to be. And so depending on the datum's intended use, with the North American datum, it's obviously going to be tied to our local plate, the North American plate, while the WGS, which we'll get to here in the next slide, that's going to cover the entire world. So that's not going to be as sensitive to local shifts. So it just really depends on what the datum is intended to be used for. All right, so ITRF and WGS datums. So outside of the surveying world, these are all what's used almost 100% of the time. So these are global datums. This is what you're probably using on your phone all the time. This is what you see the coordinates on Google Maps. This is used in almost every application. So you probably see WGS 84 a lot, but you want to see ITRF along with it as well. You might wonder what the difference is, and effectively there is no difference. Kind of similar to how we're referring to as datum and GCS are used interchangeably most of the time, but technically like the datum is a part of a GCS, it's an input to the GCS, it's one of the parameters. This is kind of the same thing with ITRF and WGS. So ITRF is the International Terrestrial Reference Frame. And as the name suggests, reference frame, it's just the origin point, the center pole, that Z-axis we were talking about earlier, and it just defines where the WGS's origin is. So it's just effectively the same thing if you ever see them next to each other, but you do have to make sure the years line up. You see in the next slide, I describe how they match up and everything. So that would be the only difference if the numbers don't match. But as far as the datums themselves, they're practically equivalent. So just see them. If you see ITRF, it's WGS. If you see WGS, it's ITRF. So originally, as I kind of alluded to before, the ellipsoidal center was off by about 2¼ meters. Because technology wasn't the best at the time, it was first constructed primarily just from Doppler radar. It wasn't perfect. So eventually technology progressed and we started using GPS baselines. We shoot lunar lasers at the moon, get reflections, information that way. Lasers from satellites, Doppler again, as well as a whole international system of control stations. And we're able to get a much better estimate of the center of the planet, the center of mass. And we were able to determine that it was off by a little bit. So originally, actually, I think I'll cover that in a second. But yeah, originally, North American datum and WGS were using the same exact ellipsoid and were practically equivalent. But then we discovered this offset. And spoiler alert, WGS adjusted, North American datum did not. And so now we're going to see an offset. Yeah, so again, these slides will be posted if you ever want to reference these numbers right here. The 2013 right here, this is going to be the most commonly used realization of WGS, which is the 1762. And that's going to be equivalent to ITRF 08. You can see within about a centimeter accuracy. So for a lot of WGS and ITRF applications, the accuracy is actually going to be probably closer to at least a foot or more. With more survey grade applications, we're going to be using North American datum most of the time. Obviously in North America, if you're in a different country, you'll be using your own local datum, and we'll get to the reasons for that in a second. So NAD83 versus WGS. So yeah, local versus global datum. Though technically NAD83 is based on an ellipsoid, and it technically could be used around the planet. It's really just intended for North America. It was tied down using control points across the continent. And so they were both released in about 1987, and they started off as equivalent. There was really no conversion required originally, just kind of like how WGS and ITRF now, especially given the technology at the time, accuracies were lower. So ITRF was introduced, shifting this reference frame about 2.24 meters, because they discovered the center of mass was slightly different. So that's what ITRF refers to, is just this new center of mass. And so the original ellipsoid, GRS 80, was not shifted. And it's also fixed to the North American plate. And so this means not only do we have that initial offset from that 2.24 meters, with it also separating for about a centimeter and a half or so each year. If you look over at this bottom image, you can see this is the same exact coordinate plotted. So I just took literally the same exact coordinate pair, same numbers and everything. And I just defined one as NAD83 and another as WGS. You can see there's about a meter offset right here. So, that's the effect from that 2.24 meter shift. And then we'll get to it a second here. We'll cover the time shift as well. So yeah, about a centimeter and a half per year. So if you ever see about a 1 to 2 meter offset, it really depends on your area. Over here in Arizona, it's about 1.5 meters or so. But yeah, if one point is offset by about that much, usually to the northwest or southeast, depending on which way the error is, you'll probably have some sort of datum error. And as long as you have the correct metadata in all your data, you should be able to easily correct that. If you do not, you might have some issues, but we'll show you how you can collect all the correct metadata here in a second. Yeah, so NAD83 2011, this is the newest realization. So it says improved accuracy. It's updated with all the control points. This is the latest and greatest. This was released in a little bit past 2011. And this is used heavily with GPS controlled points. So instead of using leveling techniques like way back in NAD 27, this is all GPS corrected, using mathematical models. A bunch of all the latest and greatest fancy techniques. So if you're using RTK, you're almost certainly using NAD 83 2011, at least here in North America. And as I was talking about the plate is shifting, well, when you're using RTK, the base stations are shifting as well. So really the whole datum is kind of moving along with you. So this means it's static datum. So the positions of features do not change with time. So if you go to a specific monument, as long as your base stations are shifting along with you, you should have the same coordinates, because it is all fixed to the North American plate. Sometimes you'll have more local shifts in really geographically, tectonically active areas like California, but for the most part, it should not change. So you can see right here at the bottom here as well, this is just another example of the difference between WGS 84 and GRS 80. Again, GRS 80, that's just referring to the ellipsoid that NAD 83 is using. So GRS 80 is just like the North American datum essentially. And the major axis is actually the same. It's just the flattening factor that we were talking about before. It's just slightly different. You can see most of the digits line up, but just that slight difference is enough to cause about that 1 to 2 meter error, or not error necessarily, offset. Just kind of covering different ways that that ellipsoidal coordinates are collected. I'll just go for this really quick. So I've mentioned it a couple of times, the geodetic datum. So the only difference between geodetic and geocentric is that you're measuring your degrees in latitude or longitude, not from the center of the Earth necessarily. If you look at this nice exaggerated model over here on the right, so the geodetic latitude, you're just measuring it just perpendicular to whatever the ellipsoidal surface is in your area. So this does create slight differences in both ellipsoidal height as well as your just degrees in general. You can see it's not going to be nearly that significant in real life, but yeah, almost every coordinate system is a geodetic latitude, so you're just collecting perpendicular to the ellipsoid in your area, not geocentric. Geocentric is very rarely used. So if you're ever wondering how those degrees actually work, since they would be the same if we were on a spherical planet, but since they're not, we're just going straight down at the ellipsoid. So especially when we jump into heights here in a second, that's a very important concept to remember, that we're collecting everything just perpendicular to the ellipsoid that we're on. All right, so I think we got our horizontal coordinates down. If not, definitely throw us some questions in the chat. We can go back and cover all that if you have any additional questions on that. But now we have to cover our heights, our third dimension here. So a lot of people aren't as interested in heights, but it's definitely worth collecting because you might be in the future. But yeah, so ellipsoidal height is just going to be the distance between wherever your GPS is and the ellipsoid surface. Again, straight down, perpendicular to the surface. It does not account for any local conditions. So if you're on a mountain, it doesn't account for that. If the gravity is different in your area and it's kind of bending the Earth's surface up and down, it's not accounting for that. It's just a nice, simple model that computers like to use, and it makes your GPS run much faster and makes your calculations go much faster. It's just the most efficient way to do GPS observations. So horizontal datums, yeah, we're just using the ellipsoids, but with the vertical measurements, we're gonna need a little bit more detail. Since we're not taking into account any of these features, it doesn't have a lot of real life applications, practicality, just because it's not taking into account local conditions. You can see over here on the right, this is a common error if you're trying to process some, like, for example, drone imagery. This data was actually processed using ellipsoidal heights, not orthometric heights. So the ellipsoidal height is kind of on a cliff right here relative to the base map. So very common error that you'll see. So you do not want to get the two confused. Ellipsoidal heights are barely ever used outside of your computer or your GPS. So you really want orthometric heights. So how do you get these orthometric heights, or mean sea level? So you use something called the geoid. And all the geoid is just a very detailed model of gravity in your area. So the geoid is just going to have a specific number. It's just a grid that goes across the Earth, just like, you know, a coordinate system of a datum would be. But for each little area of the grid, the smaller the grid, the more accurate it is, the higher resolution it is. You're going to have a number, and that number is just going to be the offset between whatever the gravity is in that area and the ellipsoid. So if you look at this example right here, you can see the geoid is pretty far below the ellipsoid. That's what it is like in here in Phoenix, Arizona. It's about 30 meters below the ellipsoid. And all that means is that we have lower gravity relative to some other areas on the planet. So, or sorry, higher gravity because it's getting pulled in. It's getting pulled in more. So in a different area, let's say the geoid was 30 meters above the ellipsoid, then it would be much lower gravity because the gravitational force isn't as significant in that area. I think the primary factor of the geoid in a specific area is going to be the composition of the crust. So it's going to be the density of those materials that make up the crust, as well as just the volume in general, because gravity is primarily determined just by the mass and proximity to that mass. So that's all the geoid is doing, just measuring the gravity in your area. And so the reason we use this is, because I said before, those ellipsoidal heights, they're not really giving us any practical application. These geoids will tell us which way water will flow, or it gives us essentially mean sea level. I put mean sea level in quotes because geoids aren't necessarily always the most accurate, but that's really what they're approximating. So let's say something happens with one of those moon lasers I was talking about earlier, used to calibrate geodetic measurements. Let's say they turned the setting on too high and they just blew up the whole moon, got rid of all the tides. And let's say global warming got really bad and all of the ocean levels rose significantly and just eroded away all the land. Well, if that happened and the entire planet was just covered with water, then water will actually settle in the shape of a geoid. So it'll kind of undulate up and down depending on the gravity in the area. So if you just remove all other variables, nice like simple physics problem, water will just kind of settle up and down in this geoid. So that's the reason we use it. It's going to tell us the actual physics, what's happening in the area, especially if we're trying to tell like bathymetry or which way water will go. It's extremely useful. So that's the reason we use the geoid. So it's really a translation factor to go from ellipsoid to orthometric height. So the geoid we actually don't use ourselves. It's really just a translation factor. So how you calculate this to get your orthometric height, which is basically equivalent to mean sea level. So if you ever see the height of a mountain, or maybe you're in aviation and there's the MSL of the airport, of the runway, that's what we're always using. We almost never use ellipsoidal height, and we almost never use the geoid itself. We just use the geoid to get from that GPS calculation to our orthometric height that we want. So all you do to calculate it is just take your ellipsoidal height, subtract the geoid from it, just take the difference. In this case, it's negative. So let's say we subtract that 30 meters, for example, then we'll have the ellipsoidal height plus 30 meters, and that will be our orthometric height. So yeah, that's all you have to do. It's a very simple calculation. So you can see right here, it's going to be higher. If the geoid, let's say we try to take the geoid over here on the left side of the image right here, where it's above the ellipsoid, then our orthometric height would be slightly lower, just because you're taking the difference. All right, so we have three different heights, basically. So we have our ellipsoidal height. That's what the computers and the GPS use. It's really nice for satellites, not relevant to us. The geoid, it's the translation factor that accounts for local gravity in the area, undulates up and down. And then, so what we're interested in the topography. So this is going to be the surface of the land as humans understand it. It's just mean sea level. So your GPS is not going to know the topography, but you will have an ellipsoidal model in your geoid model. If you want a topographic model, you have to download like a DTM or create your own or something like that, or download a topo map. So this is really what we're just trying to measure. But the actual models that we use in our GPS is going to be the geoid and ellipsoid. So you can see right here at the bottom right, like that's the most basic spherical model, ellipsoid, and really that bumpy Earth we see over there is kind of how physics really works in local areas. It's very bumpy, and it's going to vary. That's why we use the geoid just for vertical heights. Again, for horizontal, we're just using the ellipsoid. So there's some complications. So I'm not going to get too into it as far as geoid go. I already thrown a lot of terms at you, but basically you use different geoids just for different datums. So for if you're using NAD 83, using North American vertical datum 88, and to get to that from your NAD 83 ellipsoidal height, you just use the geoid 18, which is the most updated version, and then I'll get you to NAVD 88. However, if you're using WGS 84, you can't use NAVD 88. You'll have to use EGM, whatever the most recent year is. So just making sure you're using the right geoid for the right datum. You'll have to do some translation if you're trying to go from one orthometric height to another. And it's not going to be a one-to-one thing because, as I mentioned before, that those ellipsoidal heights are going to be a little bit different because of that 2.24 meter offset. So you'll have to do some conversions initially before you go straight from NAVD 88 to EGM. So it's a little complicated. I would not recommend trying to transform between different orthometric heights. I would just transform just using ellipsoidal heights and then applying the geoid. You can always apply the geoid later. Just make sure you have that ellipsoidal height. All right, so covered a lot of concepts here. So let's actually get, like boots on the ground, actually get some practicality going. So NGS survey control monuments are placed all across North America, or the US specifically, known as brass caps, and these serve as controls for different areas. So NGS monument data sheets, they're reported in NAD 83 2011 almost all the time if they've been updated recently. Really, you want to just use the ones that have GPS control. When we go through our demonstration, I'll show you what those look like. Just gonna have a black triangle because those are the most accurate and they're gonna have an expected datum. So it's a great way to see if your GNSS is operating as expected, if your data layers are set up correctly, if your base station is working well. It's just really nice setting up on a known monument that other people have shot. And if you're making a mistake, you can see what your offset is, or whatever problem you're having. It's a great way before you go out for the day, complete your survey, that everything is working as expected. So you're also going to want to create a data layer configuration before you go out there. So no matter what data collection app you're using, if you're using our Battle Flex app, where you're just naming some points. You can be using ArcGIS field maps where you're creating some complex forms and using satellite maps and using prior existing layers to go ahead and locate. You want to make sure everything is set up properly. So you really want to avoid using transformations when possible. We've gone over a whole bunch of different variables and systems and everything today because it really gets complicated. And no matter what, if you're doing transformation, if you're trying to go from one system to another, it's always going to involve some amount of errors. Sometimes this error is acceptable. I'm going to show you how a couple of nice free tools available through the NGS website can account for that. And you can use that to go from one system to another, but it should really be avoided when possible. But just at the end of the day, if you have coordinates, you are good to go. You can always convert them later. So I would always try to save your coordinates along with so your coordinates include the ellipsoidal height as well, along with the datum and the date. That way you can always shift everything later. If let's say you set up your layer wrong, you didn't realize it originally, you have all that information in your table, your lat long coordinates along your datum and date, and you could always shift them after the fact. You can interpret what's going on. So yeah, we store all that metadata, and we actually, in our new firmware update, we actually send all that to field maps. But you can, what also we recommend doing if you are using a different third-party data collection app, we're compatible with all of them. The only thing is, though, we might not send all of the metadata over just because of how that functions. We send over a specific set of messages that are standardized, so not necessarily all of our custom data fields. So what you can do, you can just start something called a track log, and that track log will store all your information that you need and more. And it'll have that date stamp on it. So all you can, so you have that stored. It uses very little memory and power. You can just throw that in your computer, just store that as a backup. And then at the end of the day, if you realize you need more metadata, all you have to do is just reference that data point you collected in your app. Hopefully it has the date and time associated with it. Most of them do collect that. And then you can just reference it with that track log at that specific time. And since it collects a point every second, you can get your exact information on accuracy, satellites, coordinates, et cetera, at the exact moment. It'll have all your metadata after the fact. But yeah, we'll show you how to join it right away. So there's no post-processing necessary. So yeah, so just the process, what we're going to go through here, we're just going to set up a data collection layer. We're going to do it on ArcGIS field maps, but you certainly do the standalone or with any other app. We're just going to create a layer in NAD 83 2011, again, just to avoid any transformations. There's always going to be some amount of error involved, whether it's human, software-based, no matter what. It's just better to avoid those transformations, if at all possible, not always possible. we'll show you how you can actually collect RTK data in either WGS or NAD83 without, so you don't have to do any transformations. So another nice new feature we'll show you in a second. We'll locate an NGS monument to use as a control. We'll collect points with SBAS, which is just your basic, you boot it up, you just using satellites. Then we'll use RTK with those real-time corrections from a base station in NAD83 and do a raw log, and then we'll do a little post-processing with those NGS tools I was talking about. All right, so let me go ahead and switch screens really quick right here. All right, so we're over here in ArcGIS Pro. So we're going to create a data layer to use for data collection. So I'm just going to call control right here. Make sure that Z value box is checked. We are interested in Z's. We're not going to add any fields right now. Right now, we're just going to set it up as NAD83 2011. Make sure you set your vertical as well. You can add some fields over here too before you upload it. Right now, we're just doing our basic metadata points. But if you're collecting specific layers, definitely set up those fields. So now we have our data collection layer set up. I have this custom toolbox that's available on our website that'll add all of our custom metadata fields to whatever layer you want. So all you have to do is just load that into your toolbox, click run. It will add all of those extra fields that will store your geoids, your datums, your orthometric heights. Right straight out of the box, Field Maps is actually using our onboard geoid, which isn't nearly as accurate as the Geoid 18 that's used with NAVD 88. And so using these custom metadata fields, you get your correct orthometric heights instead of the lower resolution one. That's not necessarily correct for that use case. So definitely worth trying that out. Again, that tool is available on our website. So this is the NGS survey data explorer. So we're just going to find a monument. This is one in our area. So this monument has known coordinates. They're in NAD 83. Highly accurate. This is a GPS controlled monument. Again, look for that black triangle because some of them aren't as good. And someone else has shot this right here. So they took some pictures. We have a latitude and longitude. And so very well-known coordinates. Right here, I'm just checking that layer I just uploaded just to make sure it is in NAD 83. It is. So that's a very common mistake on using field maps. You might not be using the right projection on your layers. Just make sure that's correct. I'm going to pause and go back for a second right here. So what I'm doing right here is we're using point one navigation. So what point one navigation is, it's a set of base stations or a series of base stations that are set up across the country. And what they do is that they send corrections over. So these base stations are in known locations. And since they're in known locations, they can account for whatever atmospheric conditions are at the time they introduce GPS error. So the primary cause of GPS error is just that atmosphere might be a little bit different in condition that day. It's going to affect your satellite signals coming in from the satellite. So what you do, you stream in these corrections from this known spot over the internet. It'll provide a correction to your data, and you'll go from, right as you see right here, from about a 6 inches to a foot of accuracy to about a centimeter to an inch. So it's definitely recommended using. If you have a Battleflex standard, you can just load up a token to activate that mode. At extreme, it's active all the time. And then you just have to find a provider of these base stations. So point one nav, that is our partner. So it's a $99 a month subscription, but it's really nice because it's fully integrated in our app. It requires basically no setup. You don't have any credentials. Basically, your login is the Flex itself. And this allows you to collect points in either NAD 83 or ITRF. But if you don't want to use that, if you have your own network in your area, you could definitely use that as well. It's we save everything in the app. We have a nice checklist workflow. Really, all you have to do is just go to correction mode and trip RTK, and then just hit the blue button to connect. So probably can connect probably no more than 10 seconds after boot up. And then you just go over to your data collection app. So super fast and easy. But what I'm doing right here is just switching point one navigation corrections from NAD 83. We have that by default, but we want ours in ITRF. So I just switched that over, and it's you can switch those on the fly. So if you want some points in NAD, some in ITRF, you can just switch back and forth between those. So if you have some data in WGS or ITRF, again, equivalent, you can go ahead and just collect with those, but with the high accuracy you get from RTK. So for most RTK options, you cannot do that in real time. So might be nice for some applications. So we're just going to collect a point right here. First, start a track log, so we have all that metadata. So we're just collecting a point on our monument. Then we're going to connect to 0.1 nav to get those RTK corrections. Looks like it just connected. You can see that RTK fixed in the top left and where that data is streaming in. We're going to collect another point just as a reference. Again, all we're doing here is just collecting control. And then we're going to go over to field map. So this is our new little function right here. So all I did right here. So what we're doing here is just sending all that metadata over. Originally, you could use field maps. We're fully integrated with the Battle Flex and field maps, but we weren't necessarily sending our complete set of metadata over. So now with this, we can actually flow points over. And so all it is doing right here is just asking you to set your pole height and your orthometric model using the geoid that we just discussed. And we can send all that information over. So I just turn this on. We're going to switch over to field maps really quick and collect a point. We're just going to configure our settings, make sure those are correct. Set up our profile right here. If you use an RTK, you can set that up. And all that profile does is just converts your coordinates from whatever datum you're in to whatever datum the layer is in your map. So if those are different, definitely go ahead and adjust that. So I just collected a point right there. You can see it switched back to our app and then it went right back over. And then we filled in all that information over here on the left. And all that metadata is filled out from datum, accuracy, geoid, et cetera, all that information's there. So now we're done collecting our points right here. We can post-process a point. So how this works is that you shoot a raw log. So a raw log is just a whole bunch of raw satellite data that we collect over the period of 15 minutes. And you can post-process after the fact using this tool called Opus, available on the NGS website or NOAA website specifically. And what this does, it references it with a whole bunch of those base stations that I was talking about in your area. And then it will account for those corrections and then go ahead and process your point. And you get an output point in both NAD83 as well as ITRF 2014. So these can be held as truth. Ignore these accuracies right here for the specific time. The base stations weren't very close, but in most cases, you should get a much better accuracy. And then you can determine how well your RTK is working at the time. So I would really go ahead and combine the data sheet that we looked at as well as the shared solution and use all that information determining how accurate your point is. So what we're doing right here, we're just taking our points that we collected and we're going to submit it into a couple of these NGS tools. So this one's called NCAT. It's very useful for switching between different realizations of NAD83. So this one right here, we're just going to upload that data file. And then what it outputs is a whole bunch of state plane coordinates as well as UTM. And you can transform it as, again, between different realizations of NAD83. It does not work from going to WGS to NAD83 though. So we're going to use a different tool called HTTP, the horizontal time displacement tool, also available from the same website. So we're going to go over there. We're just going to go ahead and choose our file, just a simple CSV with the lat, long, and ellipsoidal height. We're going to go ahead and choose our datums we want to transform between, the dates of the epochs, and right here you can see our transform points show up on the screen. So how are we doing on the time right here? Oh, this is definitely going much longer than I thought. Feel free to email me if you have any questions. Sorry about that. But just kind of wrapping it up here. If you do collect some points and you see an offset between the base map and your points, do not worry because the base maps frequently are not incredibly accurate. And also you might be using a different datum. So base maps are great for using as reference points, but you do not always want to use them as absolute truth. So as long as you have those numbers in your metadata, they do not lie. As long as they have the context of the datum, the accuracy and everything, and the date, you can have all that information ready to go. But just rely on the points, GNSS observations, not necessarily the base map. If you do need a higher quality base map, you can shoot your own with the orthomosaic using drones, as well as different private providers. So just to make things more complicated, I'm not going to spend too much time on this, but we have our different datums. So we've seen all these years attached to it. So there's different realizations. So not only do these different new realizations, like, NAD 83, the original versus the NAD 83 2011, they have that technology improvement to make the whole model more accurate, but they also account for the shift in the land tectonic plate. So the easiest way to visualize this, in my opinion, is just the creation of the Hawaiian Islands. So what happened right here, you can kind of think as this this magma chute right here as just a set of GPS coordinates. The GPS coordinates, they originate from space and the satellites, so they're not really moving with the land necessarily, at least in the the worldwide system. So what's happening is the land is shifting in a certain direction, and you can kind of think of these as older points. So like Kauai right here, or Oahu, these are like the older points that are moving along here as the tectonic plate shifts. So that's the way I like to visualize it. The North American plate moves. So if you had the same exact coordinates, but you collected the point 20 years apart, you're going to have a northeastern offset, just because that tectonic plate, you can kind of think of it shifting underneath you at a rate of about a 1 inch southwest or so per year. So that HTDP tool that I showed you, I'm available on the NGS website, that you can adjust for the shift. Again, with NAD 83, since it is tied to the plate, you don't have to worry about it. But with WGS 84 points, you do, because the planet is constantly moving, living, breathing place. From year to year, maybe 1 year to the next, not a very significant difference. That's depending on your area. But when you talk about a decade or more, it definitely adds up. You can see right here, WGS 84 and NAD 83 are diverging by about 1.5 centimeters per year. So yeah, transforming between datums, just real quick here, there's 7 main parameters. So you're just adjusting for the X, Y, and Z, the rotation on all those axes, as well as the scale itself, just the size of that ellipsoid. If you're doing the time as well, then you can double everything, so you have to account for time, the difference between everything. Again, just to recap of those NGS tools, NCAD is used for transforming from NAD 83 to a projection or a different version of NAD 83. Use that HTDP for everything else on the NGS website. And if you're trying to go from NAD 27 to NAD 83, just don't do it unless you're comfortable with some error, just because NAD 27 was based on a very old ellipsoid. And just wrapping it up here, projections, kind of just tying it all back together. So yeah, state plane, UTM, it's all based off these datums. You can kind of think of a projection as just shooting a bunch of light through a specific kind of shape, a projection plane, onto this planet, onto the datum. So different projections are based on certain different datums. So if you have one projection based on WGS, another based on NAD, they're going to be offset a little bit, as well as every projection has a different origin point, but they are completely necessary if you try to do any linear measurements, and if you're making a 2D map or anything like that. Again, use NCAD if you're trying to do projections. Yeah, so that basically wraps everything up. Definitely feel free to email me for some questions in the comments. This will be uploaded on the YouTube channel. You can definitely comment on there. Sorry, I ran way over time. A lot of stuff covered today. I appreciate everyone for joining. And yeah, we got a couple minutes left here, or no, we don't, but we have a minute or so left here, and I'm willing to stay a little bit over if anyone has any questions. I appreciate everyone. Thank you.